Okay, we had left off in our discussion with organic chemistry after showing how to name alkanes. So we had covered naming of alkanes. What's an alkane? Again, only carbon and hydrogen and only single bonds. They are the simplest of organic compounds. Now, the way you name them, based on the length of the longest chain. If your longest chain is 10 carbons in a row, it's named as some form of decane. If your longest chain is 6 carbons in a row, it's named as some kind of hexane. Now, a couple of examples we worked through. We took a look at this guy here. Longest chain is 1, 2, 3, 4, 5, 6 carbons long, but that makes it a hexane, but it's not hexane, it's hexane with this extra thing. If you have the longest continuous chain and you have something else, that something else is referred to as a group. A 1 carbon group is a methyl group. A 2 carbon group is an ethyl group, etc., etc. But the most you'd ever have to worry about in this class is either methyl or ethyl. So it's hexane, but it's not really hexane, it's 2-methylhexane. So it's hexane with the methyl group here. Here's your methyl group in position 2. The way you number the chain, you start numbering it so that the first appearance of a group gets the lowest possible number. So we've gone through that example. Now, let's take a look at a couple of more examples for you, because this does show up on the final exam, this sort of thing. If you had to name this alkane right here, what do? You look for your longest continuous chain, which in this case is 1, 2, 3, 4, 5, 6 in a row again. So 6 in a row. This is going to be some type of hexane. And again, you have a couple of groups. You've got yourself a methyl group here and another methyl group here. So this is a couple of methyl groups right there and right there. Now, some people, when they first start doing this, want to say, oh, 2 carbons, we'll call that ethyl. No, no, no. It's a methyl group and another distinctly different methyl group. Now, the way you're going to name this is dimethyl. So this is going to be dimethylhexane. Di, of course, means 2. We have 2 methyl groups, hence we're going to name it dimethylhexane. But of course we have to say exactly where those methyl groups are located. Do I number the chain 1, 2, 3, 4, or should I go this way? 1, 2. Oh, I'll go that way, because that way the first branch point, the first appearance of a group, gets the lowest possible number. 3, 4, 5, 6. So it's not just dimethylhexane, it is 2, 3 dimethylhexane. So this is 2, 3 hyphen dimethylhexane is what you would call that compound. And again, that's about as deep as we'll go for anything on the final. If you can recognize a methyl group, you can identify the longest chain, you should be fine. So that was a little review on the nomenclature with organic chemistry. Now, the next thing we have to cover here is a quick look at classifying organic compounds by so-called functional group. Organic, if all you had in organic, if the only thing you ever dealt with in organic chemistry was carbon and hydrogen and single bonds, you'd just have alkanes, and the world would be a really boring place chemically. Alkanes can be very interesting sometimes, but to most organic chemists, alkanes are boring as all get out. Mostly what humans use alkanes for, we burn them. Gasoline, things like that. We use them for fuel. Now, when you get into more functional groups, there's more diversity, more different types of compounds, and you get into living systems, and that's where it all gets kind of fun. So, the simplest type of organic compound is classified as an alkane. Only carbon and hydrogen, and only single bonds. Now, what can you do to make life more interesting? Well, instead of having carbon-to-carbon single bonds, we can have carbon-to-carbon double bonds. That compound, anytime you have a double bond, those types of compounds are called alkenes. Well, okay, alkenes are interesting. When you take organic as a class, usually it's structured with, you'll have a chapter on alkanes, followed by a chapter on alkenes, then you'll have a chapter on alkynes. It goes through all the different functional groups one by one, chapter by chapter. Each chapter will tell you what their properties are. If you're in the chapter on alkynes, how do you make them? What are they good for? Where do you find them in nature? How do they react? Things like that. So, single bonds, classified as an alkane. Double bond, that type of compound is an alkene. If you have a triple bond, it's called an alkyne. Old joke in organic chemistry, it takes alkynes to make the world. Oh well, old joke. So, those are the three simplest functional groups where all you're dealing with is carbon and hydrogen. Well, you can't really go to a quadruple bond. All you can ever make are triples. So if you want to make the world more interesting, you have to use other elements. Nitrogen, oxygen, phosphorus, sulfur, any of these halogens here. Now, you start putting those in, you get more interesting compounds. We have haloalkanes. That's where you've replaced a hydrogen with a halogen. That's supposed to be Br, bromine. So those are an interesting class of compounds. I could go on all day about any class of compounds here. They're all interesting in their own right. So if you replace a hydrogen with a halogen, haloalkane. Now, the next class would be the alcohols. Alcohols are super important. Guys, alcohols, some of the most important compounds out there. Basically, you replace a hydrogen with an OH group. So it's an OH group. This one, the carbon group, is an ethyl group, hence is called ethyl alcohol. That's what's found in alcoholic beverages. Also, it's mixed with gasoline because it burns well as a motor fuel. So ethyl alcohol, sometimes it's referred to as ethanol. So alcohols, there's a lot you can do with alcohols. Organic chemists love alcohols because we can change them into all kinds of different things. Now, if you have an oxygen, but the oxygen's not OH, it's an oxygen stuck between two carbons, then it's an ether. Ethers, very, very flammable. Typically, ethers are incredibly flammable, somewhat dangerous. I wish I could tell you more and more examples of different interesting ethers. For what it's worth, this one, ethers, the diethyl ether would be if you have two ethyl groups. This one is worth mentioning historically. That would be diethyl ether. It's an ether because the oxygen is stuck right between the two carbons. You have an ethyl group and another ethyl group. What's the historical significance? This was the first compound used in operating rooms to put people under. Before the development of diethyl ether, if they had to do surgery, they just got you drunk, gave you something to bite down on, and they tried to work really, really fast because you were typically awake while they're doing surgery on you. Diethyl ether, you breathe it in, you pass out, and then the surgeon can work at a slightly more relaxed pace. They don't really use diethyl ether anymore. It leaves you awfully groggy. It's a little dangerous. The big hazard with diethyl ether, incredibly flammable. They had instances where the patient survived the surgery, but then there would be an explosion or a fire because the stuff's so dang flammable. So survived the surgery, didn't survive the fire. Anyway, those are ethers. Next category here, the ones you should definitely know, alcohols. Alcohols are so common, where you have a carbon hooked onto an OH. Amines. Amines are very, very important. An amine is simply, you have a carbon hooked onto an NH2 group. That would be an amine. This one's methylamine. If you're a Breaking Bad fan, they had several episodes devoted to their finding a proper supply of methylamine to make crystal meth. Most of the pharmaceuticals you've ever used, any of the antibiotics, anti-inflammatory, not all anti-inflammatories, but antibiotics, any narcotics you've ever used, antidepressants, just all the range of pharmaceuticals, almost all of them happen to be amines. For some reason, when you put a nitrogen into an organic structure, quite often it has some profound effect on the human body. So most pharmaceutical compounds, most drugs happen to be amines. Anyway, what do you got to know about amines besides that? Amines are slightly basic. As a compound, they're basic. That is, they release hydroxide ion. Anything that spits out OH is a base. Now, you might look at an amine like this and say, how can that possibly spit out hydroxide? It doesn't even have an oxygen in it. Oh, if you add an amine to a solution of water, what happens is this nitrogen reaches out, plucks the hydrogen off. Notice how after it reacts, it's NH3 with a positive charge. So it's ripped this hydrogen off, leaving OH. So amines are slightly basic. Typically amines taste bitter. Quite often they stink. There are some amines out there with horrible, horrible odors you don't even want to ever experience. Some of them there's one called putrescine, if that tells you anything. Putrid is god-awful smelling. It's what putrid means. So there's one named putrescine. There's an amine that's named cadaverine because it smells like rotting cadavers. You get the picture. They're not pleasant compounds to smell. So, alcohols, you have an OH at the end. Amines, they have an NH2 at the end. Now, some other functional groups we've got to take a quick look at. There's a whole slew of functional groups. There's a whole bunch of them that contain this particular grouping where you have a carbon and a double bond to oxygen. Now remember, carbon gets 4 bonds. So if you have this C double bond O, you can put different things on either side there. Well, the way they're classified is based on what's living on either side here. So there's going to be a lot of different functional groups based around that special carbon. If you got that special carbon here, should be a bond in there. If you got that special carbon, your C double bond O, and on one side you have an H, just an H, then it's called an aldehyde. If you have that C double bond O, and on both sides you happen to have a carbon, then it's called a ketone. This would be the structure of the chemical name is propanone, but most people just refer to it as acetone, which is nail polish remover. So this is the stuff you want to take the polish off your nails, or if you happen to glue your fingers together with super glue, not that I've ever done that, but if you do accidentally glue yourself together with super glue, this is the stuff you want, acetone. It will dissolve super glue. It's a great solvent. Anyway, aldehydes, ketones. When I first learned this, I kept them straight in my head because ketone has that K sound in it, and on either side of the C double bond O you have a C, so think of a hard C sound like the C in cat. Ketone. So if you have carbon on both sides, it's a ketone. Another super important one, this one definitely worth knowing, carboxylic acids. Now, carboxylic acids, a lot of students when they first start out, they mix those up with alcohols. I told you to definitely know the alcohols, right? So you have, what's the difference? They both have that OH group. The difference is, in an alcohol, the OH group is plugged into a normal everyday carbon like CH2 or CH3. You could have something like this, CH3OH, that would be methyl alcohol. So your OH is plugged into a plain old everyday carbon. In a carboxylic acid, that OH is plugged into a C double bond O. That changes everything. You'll find that a lot of organic chemistry is based on that concept of same or different. Well, plugging that group into a C double bond O makes it way different than plugging it into a regular carbon. Alcohols are quite neutral. They behave a lot like water because what is the structure of water? H-O-H. Notice your water molecule has an OH. He has it. Hey, they act like water. Carboxylic acids, well, their main chemical property is they're acids. They spit out a proton. So this one here is acetic acid. That's the ingredient you find in vinegar. The active ingredient in vinegar is this chemical. And that hydrogen there tends to fall off of the molecule as H+. That's why it's an acid. Acids are anything that can spit out H+, the hydrogen cation. And of course it leaves this guy behind. So carboxylic acids tend to spit out H+. Other properties of carboxylic acids, just an interesting one, they taste incredibly sour. Guys, lemon juice, if you taste straight lemon juice, it's very, very sour. It contains a carboxylic acid called citric acid. And that citric acid is what makes you pucker up and gives that super, super sour flavor. So most acids do taste sour, and carboxylic acids taste especially sour. If instead of ending with the hydrogen, you have that same grouping, C double bond O to oxygen, but instead of ending with the hydrogen, C double bond O to oxygen to carbon, then it's referred to as an ester. It's not an acid anymore. Clearly, to be an acid, you have to be able to spit out that hydrogen. Notice that hydrogen is the one that falls off. Look at our ester structure. Hey, we don't have a hydrogen here. Oxygen is connected to carbon. Then it's an ester. Esters are interesting compounds. They're kind of fun when you first encounter them. Most esters smell wonderful. Most of the natural fruit flavors you know and love happen to be due to chemicals which are esters. Based on the structure here, you change this structure a little bit, change this end of the molecule a little bit, but you're keeping that C double bond O to oxygen to carbon. You can make it smell like oranges, apples, grapes, grapefruit, cherries, whatever. All the natural fruit flavors happen to be coming from esters. These fruits manufacture esters, and depending on the structure, they'll make the fruit taste like a blueberry, a grape, or a cherry. So esters are kind of neat. Last one to talk about is an amide. An amide is very much like an ester, except instead of having this oxygen, you've replaced it with a nitrogen. The important thing about amides, this would be called the amide bond. Amide bond. And I just want to tell you one quick thing from biochemistry. And again, this won't be on the test, but amides are important in that your proteins are held together by amide linkages. So proteins are made from amino acids. One end of the molecule is an amine, one end is carboxylic acid. So here's an amino acid for you. Say you had C double bond O OH, CH2 and H2. This is called an amino acid. Hey, you got that C double bond O going to an OH. That makes it a carboxylic acid, right? You've got NH2 plugged into a run-of-the-mill carbon. NH2 plugged into what? That makes it an amine. So this compound has two functional groups, an acid group and an amine group. The way you make amides is you react an amine with an acid. So if I had another one of these, I had NH2, CH2, C double bond O, OH. I could get this nitrogen to plug into that carbon. You would plug into that carbon, and the resulting structure would be starting from here, starting from this H2, it would be H2 and CH2, C double bond O. That C double bond O is this guy, who would now be bonded to this nitrogen, which would then be bonded to this CH2, and that's the amide bond. C double bond O bonded to nitrogen. C double bond O bonded to nitrogen. Now, when you do that over and over again, you get a big long chain of molecules, and it's called a protein. So amino acids are these small molecules that have a carboxylic acid at one end, an amino group at another end, and you can string them together by forming these amide bonds. Now, in biology, they won't call it an amide bond, they'll call it a peptide bond. That's because they're biologists and they don't know any better. To a chemist, it's an amide linkage or an amide bond. But again, if it's occurring in a protein structure, then it's referred to as a peptide bond. Anyway, no, that won't be on the test, but just thought I'd let y'all know. Okay, last thing to talk about, organic structures and physical properties. Now, the basic thing you really got to know in organic is these carbon chains. Remember, a lot of organic involves these chains of just carbons and hydrogens. When you have just carbons and hydrogens, that's pretty much non-polar. So, carbon and hydrogen together makes for something that is not polar at all. Now, if you have something with an OH, what kinds of things happen to have that OH? Alcohols have the OH. The carboxylic acids have that OH. If you've got an OH hanging out there, OH is incredibly polar. Very electronegative, not very electronegative. So this part here is extremely polar. So in these molecules, you should know this. The carbon part is nonpolar. We call that guy typically the hydrophobic part of the molecule. It hates water. Most organic compounds hate the water. They don't dissolve in water very well. They're like oil. This is the part that makes it like an oil. Some organic compounds do dissolve in water because they happen to have this OH. OH looks a heck of a lot like the OH and hey, remember hydrogen bonding? How would this guy relate to water? If I had another water molecule here, I'll put the lone pairs in for us. Put a dot, 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 dot. Remember hydrogen bonding? Hey, this hydrogen here could form a hydrogen bond to this lone pair, so you could have a hydrogen bond here. This hydrogen could hydrogen bond over here. So these things just love the water. Basically, this is a schizophrenic molecule. This end of the molecule saying, jump in the water. I love the water, jump in the water. This end of the molecule saying, I hate water. I absolutely hate water. It can't quite make up its mind. General rule of thumb, the more hydroxides you have, the more OHs you have, the more water soluble you are. What you find, general rule of thumb, if you have one OH for every 5 carbons, you'll kind of dissolve in water. Actually, I think it's 6, yeah. So this is 1 hexanol, will not dissolve in water. Yeah, I've got 1, 2, 3, 4, 5, 6 carbons and one of these. So this part of the molecule, the part that hates the water, is 6 carbons long. He's saying, don't go in the water, don't go in the water. This part is saying, go in the, hey, who wins? He's bigger, he wins. Now, this compound, 1,6-hexane-diol, I have 2 of those things, 2 of them saying, jump in the water, jump in the water. 1, 2, 3, 4, 6 carbons. Hey, I've got 1 of these for every 3 carbons. Guess what? He wins. It's going to dissolve in water. So generally speaking, alcohols like water if the carbon chain is small enough. So if you got a small carbon chain with an OH, you dissolve in water. You got a really big carbon chain, you don't. Little discussion here from the book on soaps and detergents. We won't go into that. But that pretty much concludes our discussion of organic. Little thing to mention here, if you go on the website, got this little worksheet for you to look at. It gives you some practice with line angle notation. So given these line angle things, can you come up with the molecular formula? And of course I have the answer key on the website as well. So if you want to practice playing around with some organic structures, you can do that. Probably the more important part here on this worksheet would be identifying the functional groups. What kind of functional groups do I have here? Hey, I've got a regular old carbon. That's just a CH2 with an OH. That makes this part of the molecule an alcohol. Got that real special carbon, that carbonyl. And it's got a carbon on one side, that would be a CH3. It's got another carbon, a CH2. Hey, you got your carbonyl and you got the carbon on both sides. This part of the molecule is classified as a ketone. Molecules can be multifunctional. You can find half a dozen functional groups in one molecule. This one happens to be both a ketone and an alcohol. Hey, this one here, you got your C double bond O. You have a carbon on one side, but you don't have the carbon on the other. Oh, that's an aldehyde. The real important one you got to recognize, run-of-the-mill carbon plugged into nitrogen, that makes it an amine. Another bad joke. It's amino world without chemists. Get it? That's called an amino group. Amino. NH2 is called an amino group, so it's an amino world without chemists. Never mind. Okay. This one, oh, that makes it an amine. Here you got your carbonyl with the hard C on either side. That makes it a ketone. This one, hey, here you got your carbonyl, but it's plugged into that OH. That makes it a can't spell. Carboxylic acid. This end makes it a ketone. So those are your functional groups. Of these, which one's going to have the sour flavor? This one. Carboxylic acids always taste sour. So that's it for organic. I wish we could go a whole lot deeper. I love organic chemistry, but that's all we have for you.